Welcome everyone to the first lesson here for Chapter 8, which is on gases. Overall, all the lectures over this chapter will cover the following sections. Properties of gases, the relationship between pressure and volume, which is Boyle's law, the relationship between temperature and volume, which is Charles's law, the relationship between temperature and pressure of gases, which is Gay-Lussac's law, the combined gas law, volume in moles or Avogadro's law, the ideal gas law, and then finally partial pressures or Dalton's law. So one thing we definitely need to understand when we're discussing gases is the kinetic molecular theory of gases. It's kind of what helps us understand really all of the properties. And so in this you see the first rule says a gas is made up of small particles that move at high velocities in random directions. That's what the picture over to the right is trying to show, with those streaks behind the balls or the gas particles. It's supposed to indicate they're moving fast. They're also going to move in random directions. Now, any sample of a gas is going to have, not thousands, not millions, but maybe quadrillions and quintillions of particles of any gas, especially if it's in, a high percentage of it being that gas. And when you have that many, and they're all moving around, and they're all moving around at high velocities, they're going to overall appear to be moving in random directions. They're also going to move in straight lines. They're not going to move in arcs. Like if you throw a ball, it moves in a parabola. These aren't going to do that because they're moving so fast, and they themselves are so small and have such little masses that gravity is not really affecting them appreciably under the situations we're describing in this chapter. Second, attractive forces between these particles are usually negligible. They, again, are moving so quickly that they have a lot of kinetic energy, which is 1/2 the mass times the velocity squared. And when I mean they're moving fast, I mean they're moving very fast. Some of them a kilometer per second kind of a thing. So very, very fast. Next, they also have an incredibly high momentum, which is that equation there. So things with a lot of momentum typically are not like explicitly or overtly affected when they collide with something else that doesn't have much momentum. Like think of a train as it's hitting a basketball or something. If a train were to collide with a basketball, the train is moving even only 15 miles an hour, the basketball would do nothing to the trajectory of the train. And both of these properties are using velocity in them and the mass. So those have a part, but they're moving very fast. And it's just, if you kind of think of like bowling balls, if you play pool, when two balls hit each other, they collide and bounce off. Eventually they slow down and stop, and that's due to friction on the surface, friction of the balls when they collide. That's why you hear them hit. We're making the assumption here that when particles of gases collide, there is no friction. Again, they're so small. The atoms technically repel each other because the outer surface of them is all electrons, and so they really don't want to collide and do much with each other. It's not to say they never do, because they will. Gas particles will collide and cause chemical reactions. It's not unheard of. It's very common, in fact. But for the vast majority of gas particles, they're either not colliding at all because they're so small and so far away from each other, or when they do nothing. Rule 3, the actual volume occupied by gas particles is extremely small in comparison to the volume of the gas, that the gas occupies, I should say. And that would definitely be true. If you think about a sample of like liquid water, 1 milliliter of liquid water, when it's boiled, is going to be 10 to 100,000 times less dense. Just using something I found online, it's roughly 43,000 times less dense as a gas So 1 milliliter of water would take up about 43 and almost 43 and a half liters. Now that's a doesn't seem like that much of a change, but we're talking about 20 drops of water is about a milliliter. So one of those 20 drops of water going up into almost 43 and a half liters of a gas. So the volume the gas occupies is way bigger than in the liquid state. And then we're talking about here, when we're talking about the volume of the particles, then it's even bigger, because gas particles, we're talking about things on the nanoscale or picoscale for some things. And so they're very, very small, and the volume they take up is huge. Another way of looking at it would be the size of the particle versus the size the gas takes up. And so, like, if I looked at the size of a molecule of hydrogen, and it's 289 picometers, which is 289 trillionths of a meter. Now, if I had a mole of that gas, it would be, as we'll see later on in this chapter, about 22 and a half liters for 1 mole of that gas. So the size difference is pretty vast. If you had a mole of a mole of molecules of hydrogen, they would take up approximately 7.6 times 10 to the negative 6th cubic meters, just the atoms. But as a gas, they take up, again, 22.4 liters, which is 0.0224 cubic meters, and that ends up being a difference of about 3,000 times. So the gas takes up 3,000 times more than that's approximate, than the atoms or molecules themselves, at least for hydrogen. And the bigger the molecule or the bigger the atoms, the less that would be. But to put that into perspective, if you had a regulation size basketball, which has a diameter of about 9.5 inches, the nearest other basketball, if they were gas particles, would be about a half a mile away. So that's how big, like, the gas would be. It's just so, like, the molecules are so insignificant compared to the size of the gas per se. So that's step 3 there. Step 4, gas particles are in constant motion, moving rapidly in straight paths. I already mentioned that. And then 5, the average kinetic energy of gas particles is proportional to the Kelvin temperature. First thing we need to look at when we're talking about the properties of gases will be specifically pressure. So what is pressure? Pressure for a gas, or really anything, pressure is equal to a force divided by a surface area that the force is being applied to. Like, I'm sure you've all heard that, like, you can sleep on a bed of nails. Stepping on a nail, basically you're gonna puncture your foot, because you're putting all of your weight, and weight is a force. You're putting all of your weight onto a very small surface area, the point of a nail. Now, if you take all of your weight and you spread it out over thousands of nails, it ends up being very little weight per nail. Even if you weighed 200 pounds and you stepped on one nail, you'd be putting 200 pounds per a very small surface area, something you can't measure because it's a point. But if you divided that by 1,000, let's say because you had 1,000 nails, now you're only putting 0.2 pounds per nail, which is a very small number. That's only like 90 grams. Yeah, and that might be enough to still puncture you if you weigh 200 pounds. I don't know off the top of my head what the strength of someone's skin is. I've never looked that up, because that would be certainly part of it, and every nail is slightly different. But I'm sure a bed of nails has at least 1,000, if not more, nails to really spread that out. So pressure is force divided by surface area. And so what happens is for gases, as they're moving around, let's say we have them in some sphere, and you've got these gas particles like right up in here. They're moving around, they're bouncing around, and they're hitting the walls of it. Well, like if this was a gas particle, they're moving in straight paths and hitting the walls of that. Every time they collide with a wall, they're imparting a force. And based on the size of this particle that's actually hitting right here, or I should say, I should do this in a different color, as they're hitting right there, the size of that impact and how hard they hit determines the pressure. And so if you think of a balloon being the thing the gas is contained within, this is my balloon. The reason that when you blow into a balloon and you seal it off, the reason they stay inflated is because you've got these gas particles, literally just bouncing around and hitting each other. So they're going to hit there, then here, and here. And like I mentioned, you've got quadrillions and quintillions of these things hitting in there at the surface of the balloon at really all times. They're moving very fast, and there's a whole bunch of them. And that's what keeps the balloon inflated. Now, if you pop a hole into it, then gas can escape, and now it's not going to be inflated anymore. So the bottom of this slide shows here atmospheric pressure, and that would be considered what the average pressure in Earth's atmosphere is at sea level. So some typical values for atmospheric pressure are listed down below there, but it's 1 atmosphere. It's just a standardized value. Just they set it at 1, and they call it that unit of pressure atmospheres. It's also 760 millimeters of mercury or 760 torrs. You might see or have seen millimeters of mercury used in like a doctor's office when they take your blood pressure. Like let's say your blood pressure is 115/80. Those numbers are in millimeters of mercury, and I'll get into this all later on in this chapter, but for now, that's just what, that's an example of when that's used. 101,325 pascals is, or 101.325 kilopascals, that's standard atmospheric pressure. That's actually in the SI units. They give it a new name, but using the SI units, the standard ones, it's 101,325. And then in pounds per square inch, or PSI, it's 14.696. The next things we want to talk about when talking about gases and their properties are volume and temperature. So volume is just the amount of space the gases take up in 3 dimensions, and temperature is essentially a correlation to kinetic energy, which again is 1/2 mv squared. As you increase the temperature of a gas, you're not changing the mass of the gas, and so what happens is they move faster, and they move faster by squaring the velocity, essentially. And so temperature is an indirect measurement of kinetic energy of gases. The next thing to discuss when looking at properties of gases is the amount of the gas. And the amounts of anything in chemistry are measured in moles. So that's what the symbol N there means, is moles. And as I'm sure you're aware, if you have more moles of a gas, that gas is going to take up more space. You're increasing the amount of gas. Like you blow up a balloon, it gets bigger because there's more gas particles in there. So I mentioned it earlier, typical measurements or typical units of pressures of gases, and I had atmospheres a couple slides ago, but as a reminder, the atmosphere is considered the average pressure at sea level on Earth, which, as the little prompt there says, it's 1 atmosphere, and that is a unit of pressure, atmospheres. So the table here shows a description and a typical units of measurement for each of these properties. Pressure, again, is force exerted by a gas against the walls of the container per unit per amount of surface area. The units there would be atmospheres, millimeters of mercury, torrs, pascals, psis as well. Bars is another one you might see. Volume is measured in milliliters or liters. It's the three-dimensional space occupied by a gas. Temperature is the determining factor of the kinetic energy of gas particles, measured in Celsius or Kelvin. Kelvin is required in calculations, as it says. The amount of the gas measured in moles. We can measure the amount in grams, but it has to be converted into moles when doing calculations. The table here just shows, again, a more comprehensive list of the different measurements of pressure: atmospheres, millimeters of mercury, torrs, inches of mercury, pounds per square inch, pascals, and kilopascals, and then what their typical values are on Earth at sea level. The pressure of a gas is measured using a barometer, which is this device over here. At least that was the original, first invented form of the barometer. And so what happens is, in the barometer you have mercury, liquid mercury. You fill up a glass tube right here with liquid mercury all the way up, and then you invert it, like you'd put your thumb over the top of it so none of it leaks out, but you invert it into the pool of that liquid mercury. The weight of the mercury is going to cause the height of that liquid to fall down. So it's falling down, and as you might be aware, weight, which is due to gravity. Weight is kind of like, again, equivalent to gravity. And so gravity is pulling the mercury down. Now, it just so happens that if you have this in an atmosphere, there's gas particles floating around. Those gas particles, let's say that's one right here, they are going to push down on the pool over here, in front, behind, all of that. And what those are going to do is cause the liquid mercury also to rise up. So you have these competing, opposing forces. You have the atmospheric pressure, which again, pressure is force over a surface area. And then you have the gravitational force, the weight of the mercury pulling it down. At some point, those forces will equilibrate, they will equal each other, and therefore there will be no net force on the mercury, and so it will stay at whatever height that is. At sea level, the average height for this is 760 millimeters. And what that means is it's above the surface of the liquid. So if you take a ruler to the mercury and you put it at the 0 millimeters right there, and you have it rise up, it would be approximately 760 millimeters tall. Now, I can't actually show this ruler as being 760 millimeters, but we can imagine that if we had started it right there and then right there, this distance would be 760 millimeters, or it's like jumping over to the ruler. It'd be 760 millimeters tall, or 76 centimeters, so slightly less than 1 meter tall. And now you could convert this into inches, and just to show that, we can do the math, but 760 millimeters, which equals 76 centimeters, if you divide that by the conversion factor of 2.54 centimeters per inch, you get approximately 29 inches in there, 29.92 inches. You might be familiar with something around 30 inches when talking about pressure, because if you ever look at a weather report, they'll give you the barometric pressure, and in America, since we use inches, they will do that. And so 30 inches would be basically the average pressure, but pressure can go up above that, pressure can go below that, and it turns out that the atmospheric pressure has an impact or has an effect on weather patterns. So the slide here just shows different pressures at different altitudes. What I haven't mentioned yet was that atmospheric pressure does depend on your altitude. And the reason is, let's say you were standing on Earth. All right, Earth is, zoom in, it starts to look flat, doesn't it? Isn't that weird? It's crazy. But let's say you're standing right here on the surface of Earth. At that point, you're going to have all of this air. No, I can't. I gotta do it right. You're gonna have all of the air from space to yourself, weighing down on you, literally weighing down on you. And so here we go. I'll color that in. That's the air, and all of that is pushing on you. Now it turns out, on average, look how small it is. You can't even see it now, but you're there. On average, the average person has, like I had written before, in American units, the pressure is 14.696 pounds per square inch. So every square inch of you, let's pretend this was an inch by inch dimension. Every square inch has, if I'm rounding up, 15 pounds. I've done the math. The average male is going to end up having around like 45,000 pounds of just air pushing down on you. And the average female is going to have like 35,000 pounds, much less, because men are bigger than women, generally speaking. And so there's a lot of air pushing down on you from above. You could think of this like going into water. You've certainly heard of water pressure. If you go deep down underwater, there's a lot of water on top of you, literally on top of you. And so that's going to weigh you down. If you go too deep, you can get killed just from the pressure of the water pushing down on you. All right. But as you go up in altitude, so we get this guy, and let's have another person, same person. Now he's at a higher altitude. Now that person has less air above him. So the atmospheric pressure at this altitude is less than the person down there on the surface. All right, and so as we can see in this picture, you have at sea level, average pressure is 1 atmosphere. At the top of this mountain, they have 0.7 atmospheres. Here's some more in this table. The Dead Sea, which has an altitude of negative 0.4 kilometers, that means it's 400 meters below sea level. The average atmospheric pressure is 800, so above 1 atmosphere, because 1 atmosphere is 760. Los Angeles, which is barely above sea level, has an average pressure of 752. Las Vegas, which is a high desert, has an average pressure of 700 millimeters. Denver, which is about a mile high, has an average pressure of 630. And then all the way down to Mount Everest is only 250. That's essentially 1/3 the pressure at sea level. And this is why people who are trying to climb Mount Everest, they need breathing apparatuses in order to do it, because there's so little air, there's so little pressure that they just can't breathe. So this is the last thing for today's lecture. It's example 1. It says a tank of nitrous oxide, or N2O, is used as an anesthetic, and it has a pressure of 48 psi. So in this, that's our measured value. Somebody measured the pressure of that gas. That's, by the way, also laughing gas. And so the measured value here is 48 psi. We're going to end up trying to convert this pressure into atmospheres. You may remember from the earlier slide that 1 atmosphere is 14.696 psi. So that's the conversion factor we're going to use. So we don't have anything there just because psi is all going to be grouped together, pounds per square inch at the top. And now we're going to get rid of those pounds per square inch by bringing them down here. So it's the 14.696 psi for every 1 atmosphere. Pounds per square inch cancel out. And you can see, like, 48 divided by 16 is 3, so when we do this problem, we should see the pressure being around 3 atmospheres. And so when we do that, we get an answer of 3.266 atmospheres. We have to consider significant figures as always. 48 has 2 significant figures, so you're going to round 1 to, you go to the third place value, it's a 6. So that rounds the 2 up, so we get 3.3 atmospheres for that. All right, that is it for the first lecture for Chapter 8, Gases.